This is Chapter 2, Section 3. We will be breaking it up into an A and a B section. For today's lesson, we're going to talk about accuracy, precision, percent error, and significant figures, and how to calculate basic calculations with significant figures. So for accuracy and precision, make sure you get these two definitions down. Accuracy is how close a measurement is to the accepted value. For accepted value, you could use some other words in there as synonyms. So accepted value, it could be your target or your goal. Typically, we say accepted value is something you would find in a reference book. Precision is going to be how close a series of measurements are to each other. So if you were to run a lab, collect some data, how close is the data that you collect to itself, not to the target or the goal. So for accuracy, we say that is considered to be correct information. Precise is considered to be consistent information. Again, consistent measurements with themselves. If I were to draw 3 dartboards, darts has multiple games within a game, but one of the things people like to do is to make sure that they hit the bullseye in the middle. So let's say that you threw 3 darts, and on the first one, all 3 of them basically hit the bullseye. The next one, say one was the bullseye, the other 3 out here, and then the next one were just randomly scattered about. I'm going to redo that second one. For the second one, we're going to put all 3 over here together, and then for the third, they're going to be randomly scattered. So as I am looking at each of these, in the first one, because all 3 darts are close together and consistent, we say that they are precise, and they all also hit our goal or our target, so they are accurate. In the second one, they are all close together, so they are precise or consistent with each other, but they are not accurate because they did not hit our goal or target. And then in the third one, it is not precise or accurate because they did not hit the goal and they are not consistent with each other. We could also take this with a set of data. I know that the density of water is 1 gram per centimeter cubed. That's the density of water. If I asked you, and I'll write that again as my target or accepted value for the density of water. If I asked you to go and perform some tests and get you to collect data on the density of water, and you came back with values like 0.867, 0.870, and 0.871, I would say that your values are very close together, so they are precise, but they are still too far away from what the target is. If you were to look at percentages, these are a good 10% off of whatever your target is, and so they are not accurate. Not accurate. Next up, we have percent error. Percent error is going to indicate the accuracy of a measurement because we are comparing it to the literature value, which is also your target or accepted value. So experimental is your data that you collect or the data collected. The literature is the accepted or goal value of whatever it is you're looking at. These right here are absolute value signs. So if you put absolute value signs on, you are guaranteed to always get a positive percent error. But technically, you can have a positive or negative percent error. It will just let you know if your experimental values are higher than or lower than your literature values by a certain percentage. And since it is percent error, we multiply times 100 to get percent. Mathematically, when we do this, we would subtract our 2 values on top first, then divide by the literature value, then multiply by 100, and your answer would be set up as a percentage. Please write down this example Make sure that within your calculator you can get the correct answer. It says a student determines the density of a substance to be 1.4 grams per milliliter. Find the percent error if the accepted value is 1.36 grams per milliliter. So this is already plugged in your information for you, and your answer should be 2.9% error. That's not too bad. I would say anytime you're involving human experimentation in this, as far as not a lot going on with machines, if you get less than 5% error, you're doing pretty good. Moving on now to significant figures. Significant figures is something that most kids, as I've taught every year, typically struggle with. Number one, what is even the purpose of significant figures? And man, that is a lot of rules to keep up with. So, whereas your percent error was looking at the accuracy of a measurement, significant figures looks at the precision of a measurement. And that precision depends on the device that you use to measure with. So when we record significant figures, we record all of the known digits plus one final estimated digit. So I have a picture of a paper clip here. If you were to put a ruler up to it, and this ruler measures in centimeters, and I asked you to give me the length of this paper clip, well, if I go with known digits, I know that it's after the 2, and since this is in increments of 1, the smaller increments are in increments of a tenth, it definitely goes to that third increment. So that would be 2.3. I know that for sure. The estimated digit is going to come into play if I ask the entire class, well, the end of the paper clip, is it right on 3? Is it 3.5? What is that estimated digit going to be? Some of you might say a 2, a 3, a 4, a 5. I'm going to put a 5. It looks to me like it's about halfway. So based on this particular device, it will measure out to the tenths place with lots of precision. But then the estimated digit in the 100ths place, again, is an estimated value. So again, why are things like this important? If I were to bring out 3 devices that measured liquid volume, say a flask, a graduated cylinder, and a burette, the flask does not have a lot of precision with it. The graduated cylinder has more markings or scalings on it. So it'd be a little more precise, and then a burette, which you've probably never seen, a burette has many more markings on it, and it is an even more precise measurement, so I can give you more digits with it. I could also talk to you about digital balances. I can go in and I can buy one that measures to the nearest tenth or hundredth or thousandth of a gram. And I guarantee you the more precise one, which measures to the thousandth of a gram, costs a lot more money than the other 2 that are less precise. So again, significant figures are important because we are looking at the precision of a measurement based on the device you are using. So I'm going to go over with you 5 rules for determining significant figures, but basically, any number 1 through 9 is significant. So, all numbers 1 through 9 are considered to be significant. So, the only digit I'm leaving out is a 0. So, my 5 rules are going to be about zeros. Is this 0 significant or not? So, rule number 1, we call it the sandwich rule. So if a 0 is between non-zeros, so a 0 between non-zeros, so non-zeros are any number 1 through 9, that is considered to be significant. So I'm going to put a check mark for yes, it is considered to be significant. An example of this would be if I showed you 40.7, that 0 is sandwiched between two non-zeros, so I have 3 significant figures. I'm going to put SF right over here. I have 3 significant figures in that number. Rule number 2, we call it leading zeros. So any zeros that lead a number are not significant. So I will put an X right here. They are not considered significant. So in this example, 0.0087, those 3 zeros at the beginning are considered to be leading the number, all 3 of them, and all 3 are not significant. So I only have 2 significant digits in this one, the 8 and the 7. Rule number 3 is called the AND rule. If you think about the word and in your English class, and means 2 different things have to be going on for this to happen. So for the AND rule, part of that is if zeros are at the end of your number, and after the decimal. So zeros are at the end of a number and after the decimal or to the right of a decimal, then they are considered to be significant. So an example of this one would be 85.00. Well, those 2 zeros are at the end of a number and to the right of a decimal or to the right of a non-zero. So they are considered to be significant. So all 4 digits here are significant. All of them are significant. Rule number 4, we have an A and a B part. It's dealing with zeros with and without a decimal. So, part A, trailing zeros. And rule number 2, I had leading zeros. And rule 4A, trailing zeros. Trailing zeros mean they are at the end of a number with no decimal. No decimal. So if I took and these are considered to be not significant. So if I took the number that we have similar to the one above it, 85,000. I do see 4 digits. Those last 2 zeros are at the end of a number, but there is no decimal. No decimal. Because really they would be considered to be to the left of an understood decimal. Then I only have 2 significant figures. Now, again, significant figures are based on the equipment that you use to measure them. So if I were measuring the weight of a very massive elephant, a very massive elephant or car, and that car was 85,000 pounds, but my scale used to measure it was only good to the nearest hundreds place, maybe the car actually weighed 8,460 pounds or 66 pounds, 8,466 pounds, but it rounded it to 8,500 pounds, letting me know that, hey, I'm only good to the nearest hundredth of a place. So 2 significant figures, but those last 2 zeros have to hold the place to show the magnitude of the number. I can't just drop off the zeros and it be 85 because 85 is nowhere near 8,500. So they are holding a place, but they are not significant based on the device used to measure it. Rule 4B is a version of the sandwich rule with a decimal. It's a version of the sandwich rule with a decimal, and these zeros would be considered to be significant. So if I had the number 8,500 with a decimal point at the end, it is very similar to the one in front of it, but that decimal is telling me the device used to get that measurement was good all the way to the 1 spot, and the confidence in that its precision is going to be shown by me placing a decimal behind the 0. So now all 4 digits are significant. So if I did weigh a car and it did weigh 8,500 pounds, maybe 8,500.1, well, it did give me the last digit in front of the decimal with precision and threw the decimal on there. So that is sandwich rule with a decimal. So you're sandwiching between a non-zero and the decimal, whereas in rule 1, you're sandwiching between 2 non-zeros. So you have all these rules written down. We're going to look at even more examples. Okay, so in these examples, we're counting up how many significant figures that we have, and we'll also talk about which rules cover which ones. So again, all non-zeros are significant. So any number 1 through 9 is significant, so we're worried about the zeros. This 0, the rule that covers it is going to be the AND rule. That 0 is to the right of a decimal and to the right of a non-zero, so it's significant. There are 4 significant digits. In example 2, this 0 is sandwiched between 2 non-zeros, so that's rule 1. We have 3 significant figures. In number 3, this last 0 is covered by rule 4A, trailing 0 without a decimal. So that last 0 is holding a place. So I only have 3 significant figures. That last 0 is not considered one. And in example 4, we have a couple different rules going on. These first 2 zeros are under the leading 0 rule, and they are not significant. But the last 0 is covered under the AND rule. It is to the right of a non-zero and to the right of a decimal. It is significant, so I have 2 significant figures in that example. Again, please keep up with your rules and be able to practice with those. There are also many rules on rounding, but for now, we're going to go with traditional rules on rounding. In math class, if you have a number that you round up, if it's followed by a number that is greater than 5, great, you round down. If it's followed by a number less than 5, if it's followed by a number that is a 5, for now, we're just going to say go with traditional math rounding rules and round up. There are 2 additional rules that we are not going to cover. So if at any point someone's watching this podcast and they're talking about rounding rules, know that there are 2 more rules that I am not covering in this particular section for this year. Okay, let's go do some math with calculating with significant figures. So when you are doing simple multiplying and dividing, it says the number with the fewest sig figs determines the number of significant figures in the answer. So you will always hear me refer to this for multiplying and dividing. I am looking for the fewest significant figures given. Fewest significant figures given. So in this example, we've got 13.91 grams per centimeter cubed times 23.3 centimeters cubed. And there's the answer that your calculator would give you. Again, you're making sure this stuff works. In this first one, there are 4 significant figures. And in the second one, there are 3 significant figures. Well, the fewest significant figures given is going to be 3. So I'm only allowed 3 significant figures in my answer. In my answer, I start with the first significant digit, which in this case is 3. If your number was a decimal value and started with a 0, then that very first digit of 0 would not be significant based on our significant figure rules. So, 1, 2, 3. There's my third significant figure. I go with traditional rounding rules. It's followed by a 1, so it does not round up. And my final answer with 3 significant figures, because that's how many I'm allowed, is 324 grams. So for multiplying and dividing, you are allowed the number of significant figures based on your given information that has the fewest significant digits. Addition and subtraction is going to be a little bit different. For addition and subtraction, we are going with the fewest decimal places that are significant. So fewest places after the decimal. Fewest places after the decimal. So in this first example, 3.74 milliliters plus 4.1 milliliters. I have 2 places after the decimal here, only 1 place after the decimal there. So we are only allowed 1 decimal place in our answer. That 8, based on rounding rules, looks like it will stay an 8. So my final answer is 7.8 milliliters. And the next one, the first number has no decimal values and the second one has 1 decimal value. So going with the fewest decimal places, I will have to round it off right at the ones. So based on traditional rounding rules, this number would be 354 grams as my final answer. So again, we're going with the fewest decimal places is how many we're allowed in our answer. You might have 50 places in front of the decimal. We are limited in addition and subtraction by the decimal places, so any digits after the decimal. We're going with the fewest. Now, rounding it out, exact numbers do not limit significant figures. So if you counted up the number of students and got 12, those 2 digits do not limit your calculations if you make a calculation with it. Exact conversions. So when we were doing our SI conversions, dealing with the grid, the 1 and then a 1 with how many ever zeros you need, they do not limit. Both of those numbers have 1 significant figure the way they're written, but when you do calculations with them, they are considered to be unlimited. They do not limit. And then again, the 1 in this conversion is considered to be an exact number. It does not limit either. But this 2.54, that is a rounded off value. So it does have 3 significant figures if you had to use it within a conversion. Let's follow up with a couple more examples. In the first one, 15.30 divided by 6.4. In your calculator, you get 2.390625. But for division and multiplication, we are limited by fewest significant figures. Fewest total significant figures. My number is given. 15.30 has 4. 6.4 has 2, so we're only allowed 2 in our answer. When I round that off, that will be 2.4 because, again, 1, 2, 3 is followed by a 9. We round up to 2.4. In subtraction, we are limited by decimal places. So when I subtract and get 18.06, I am allowed either 1 decimal place or 2 decimal places. 1 is fewest, so we round off to the first decimal place. Traditional rounding rules gives us 18.1 grams.